This is chapter 4, side problems. Chapter 4 covers triangle inequalities. Now, page 64, side problem, try this. Yep,
Yes,
and
okay. So we see for this triangle ABC, we can use a certain theorem, which basically says that for a given triangle ABC, so if the larger a side is, the larger the angle is opposite it. So for example, let's say the three sides are ordered like this. So AB is the smallest, BC is the medium side, CA is the largest side. The angles opposite them will also, when you order them by measure from smallest to largest, will appear in the same order. So angle C is opposite AB, so it's the smallest. Angle A is opposite BC, so it is the second smallest. And angle B would be the largest because that's the one opposite CA. So we can use this in these two problems. So the smallest angle in a triangle is the one opposite the smallest side, which is 20. So angle C would be the smallest angle. And for the largest, it would be opposite the 26, so angle B. And for the second example, we have the smallest angle would be opposite the smallest side, 13, so angle B would be the smallest. And then for the largest angle, it would be the one opposite the 15, so angle A.
it's great. Let's move to page 66, another
Yes.
triangle inequality problem.
Yeah. So now for this one, we're using a different inequality. So this is the triangle side inequality. So basically for any given triangle, we have that if we pick any two sides and we add them up, it has to be greater than the third side. So this will be helpful in this problem. So let's sketch our triangle ABC. And we'll call AC, we'll call it equal X. And let's try applying the triangle inequality to all three different sides. So first, we can pick AB and BC. So add up AB and BC, 6 and 8. And that has to be greater than X. But we can also start with 6 and X. So if we pick 6 and X and we add them up, we know that has to be greater than 8. And the final one, we add up 8 and X, and that has to be greater than 6. Well, now for this one, this third one always has to be true since X is positive. So it's not going to help us narrow down the possibilities for X. But the first two will. So if we add up 6 and 8, we get 14 is greater than X. And for this second inequality, if we subtract 6 from both sides, we get X is greater than 2. So that means that X is between 14 and 2. And that means that there is 14 minus 2 minus 1 possibilities, which is equal to 11.
That is great. Thank you, Andrew. Andrew, can we generalize what you did? Just awesome job for solving this problem. Let's say A, B, C. So can we generalize that C, the third side, let's say in this case, third side, C, is less than A plus B and more than what?
The absolute value of A minus B.
That is great. Yep, that's the over generalization. That's great.
Yeah.
Nice.
So
Thank you.
that helps with problems like these, where we are trying to look for all possible integer values for the third side.
Great. Thank you. We have chapter 4, page 67. This time, our try this activity site activity is a proof. Let's see. Let's visualize the situation, Andrew, first.
Yes. So the hard part about this proof isn't how you prove it, but where you start. So we need to draw an auxiliary line.
Good.
So we might try extending AD to point E, right? Point E.
Mm-hmm.
And
That's important. Good.
from this triangle, right here,
Mm-hmm.
we get that from the triangle inequality, DE plus EC is greater than DC. And we also have this orange triangle.
So orange one, ABE triangle.
Yes, and AB plus BE is greater than AE.
Yep, that's understandable and clear.
Yeah.
Very nice.
So if we combine these two, right, what we end up with is we can divide this AE, we can divide it into AD and DE. And now we can,
AE is equal to sum of these two parts, length, AD plus DE. That's good.
yeah.
Mm-hmm.
And now we can add on EC to both sides. And we have DE plus EC. And from this first inequality here, we know it's greater than DC. So we know that this part is going to be greater than AD plus DC. And this part on the other side is AB plus BE plus EC. And the final step is BE plus EC. Well, B and C, they're collinear, so we can add them up and we get BC.
AB plus BC greater than AD plus DC. Yes, QED. That's awesome proof. Thank you, and it's perfectly understandable. Thank you, Andrew. So now our chapter 4 side problem. We have second proof from page 68. Let's see.
Yes, so we have these two inequalities in a triangle, and they're using S and P. So S is the sum of all three of the medians in the triangle. So let's draw in all of these medians. So basically, what the first one is saying is that the sum of all the medians, A, D, B, E, C, F, those add up to an amount that is less than the sum of A, B, B, C, and C, A, so the perimeter. And the second part is saying that the sum of the medians, even though it is less than the perimeter, is greater than 3/4 of the perimeter. So let's try focusing on only one of them first. Let's focus on A. So one way that we could prove A is to extend the parts of ABC and we extend each of the sides into parallelograms. So we'll call the ABC, this will be B prime, that's a parallelogram. BAC, A prime, that's also a parallelogram. BCAC prime is also a parallelogram. So now we extend the medians, and we keep in mind that they're parallelograms. And we'll need to focus on 3 triangles for this one. First, we focus on this triangle.
Okay, very
Then
nice.
on this triangle. And on this triangle. So the red triangle, if we use the triangle inequality, we have that AC plus AC prime is greater than 2 times C prime. But notice that C prime F is equal to FC, which means that this is really 2 times FC. This is 2 times FC, because C prime F plus FC is equal to C prime C. Now for the next one, the orange triangle, we have that AB plus BA prime is greater than AA prime, which is really 2 times AD. And the final one shows that BC plus CB prime is greater than BB prime, which is actually equal to 2 times BF. And now, one more thing. We can replace each of these 3, AC prime, BA prime, and CB prime. Since they're in parallelograms, we can compare it, we can equivalate it to the one that's opposite it. So for example, if we focus on the parallelogram that contains the red triangle, we have that C prime A is opposite BC. So BC. Same thing for BA prime. BA prime is opposite AC. And the final one, we have AB. So we have AB. And now, notice we can add all of these up. And we get that there's 2 perimeters here, so 2P. And then these add up to 2S. And when we divide by 2, we get P is greater than S.
So that was this first part of this proof. That's great. So now let's clean this everything and then move to the second part of the proof. Okay.
Okay, so the second part is the proof of part B. So let's quickly redraw that. Okay, so something really important about this part is that we understand that this side length right here, that is 2/3 of AD, because the medians are split at the centroid into a proportion of 2 to 1, which means that this is 2 out of 3 of AD. So we say that that is 2/3 of AD. This is 2/3 of FC, and this is 2/3 of BE. So let's focus on these 3 triangles this time. Here are 3 triangles. This red triangle, this orange triangle, this yellow triangle. So from the red, we get that 2/3 of AD plus 2/3 of FC is greater than AC. From the orange triangle, we have that 2/3 of AD plus 2/3 of BE is greater than AB. And for the yellow, we have that 2/3 of BE plus 2/3 of FC is greater than BC. So if we add all of these 3 equations up, inequalities, we get 4/3 of S. So there's 4/3 if we match them up. So these two add up to 4/3 AD, 4/3 FC, 4/3 BE. And in total, they add up to 4/3 of the sum of the medians. And this is greater than the perimeter, which is AB plus AC plus BC. And now all we have to do is multiply by 3/4 on each side, and we get what we're trying to prove.
It's great. QED. Thank you, Andrew. That was a great proof and very colorful visual proof. This is chapter 4, side problem from page 69.
Yeah. So we're going to be using remember the inequality we came up with before, which is when we have a triangle like this, A, B, C. We have that C has to be in between the absolute value of A minus B and A plus B. So this is going to be our C in this triangle. Let's focus on ABC first. What we end up with is it has to be between 8, this variable C, it has to be between 8 and 16. And from the other triangle, the 3, 7, C triangle, ABC, we have that it has to be between 4 and 10. And if we combine these two inequalities, specifically these two, we get 8 is less than C, which is less than 10. And obviously, the only integer that fits in between 8 and 10 is 9.
Wow, I was thinking that's the inequality problem and they're asking exact value. And great, we found the exact value of AC, integer value 9. That's great. Then this is the end of the chapter 4, side problems. Thank you for listening and following for the proof and this solution steps of this problem.